Have you ever seen a train that's got a ton of locomotives on the front end? What about a train that's got a ton of locomotives on the front and on the back? Maybe in the middle? Those are typically only controlled by one crew. How the heck does that work?
Well, what's up guys, this is Heiss, and today we're here at the Colorado Railroad Museum in Golden, Colorado to talk about how that works. Welcome to Multiple Unit, or MU, 101. Oh, and because I know a lot of you guys like the short answer fast, and we'll get to the details later, the way it works is that we've got an electrical cable that we can plug in that red socket between two different locomotives, or as many as you want, really. That handles all of the electronic stuff, all of the engine, the power, the dynamic braking, any of that sort of stuff. For our air brakes, in addition to our brake pipe, we'll have sets of 3 unique hoses that'll connect braking systems on the locomotives, and the engineer can control all of those things. For locomotives on the other end of the train, the locomotives are equipped with special radios so that we can operate in what's called a distributed power motor, DP. That way the engineer can send commands from the lead units back to the trailing ones, and then the trailing ones can use that same electrical connector we talked about. Now, of course, that was just the short answer, but the details are always so fascinating, so I hope you'll stick around and learn about the fun, nerdy stuff that goes with that. First things first, let's talk about how you actually get to control multiple locomotives. You make your power throttle work. It all happens with this special plug right here. This is a 27-pin plug that attaches to a 27-pin cable that runs between the locomotives. That allows the locomotives to talk to each other in every way that they need to. 27 different pins to send 27 different messages is quite a lot, and we'll talk about what they all do in just a minute. You plug in the cable on the lead unit to the trailing unit. In those sockets, you're good to go. One thing that might trip you up is that we also have dummy plugs to hold that cable when it's not in use. And a fun factoid is that this SD40T-2 here at the museum, being built in 1980, is the newest locomotive we have at the museum, but it actually still would not conform to modern day code, where there's only one dummy plug. You need to have 2 so that you're not accidentally sending signals out into the ether. You know, it's one of my favorite things about locomotives and railroading that you take a look at a locomotive and you see the parts and you go, yeah, that doesn't look that big. And then you hold the part away from the train and you go, oh, that 27-pin cable that I was talking about? This is how big the plug is. It's considerably large. You can see all the different pinouts. It's a big cast aluminum guy, 27 pins, and we'll go through what each one does in just a second here. You plug that cable in between the units, you're able to transmit every single piece of information the train's gonna need to function with only one lead locomotive that's under control by an engineer. That's it on the power side, but what about the braking side? The brakes for a train, other than the dynamic brake, are all pneumatic. They're all air-based, and you're not sending any air signals with these. So let's take a look at the rest of that. Let's talk about those 3 special hoses we have. You can see that there's a total of 7 hoses coming off the front of this locomotive. One is the brake pipe that runs down the whole train, regardless of whatever. But we have 2 sets of 3 unique hoses here that are going to attach all of the different locomotive braking systems together. Each locomotive will still get information from the brake pipe, and that'll help set up each engine's brakes. But depending on how you're handling the train, you might not want the engine's brakes to come on. So you might want to have independent control, which is part of the reason why it makes sense it's an independent brake. The 3 hoses we have are the main reservoir hose, the actuating hose, and then the independent application and release hose. Depending on when the locomotive was manufactured, the tags might say something different. This locomotive says independent equalizing rather than application and release, but the function is the same. The main reservoir hose ties all of our main reservoirs together. It means that all of our air compressors can work in sync. On steam locomotives, when you double-headed, you only got the air supply from one locomotive, whoever's brake stand was cut in. So with diesel locomotives, now you can use everyone's air compressor, which helps limit the chance of running out of air, which helps prevent runaway trains. The independent application and release hose, or the IAR hose is what it's typically called, is what actually allows the engineer to apply the independent brake on every single locomotive. Whatever he does with his independent handle will then travel through this hose and tell all the units to do the same. But in 26L, or any electronic version of 26L, which is pretty much what all different kinds of air brakes are these days, you have a separate axis of control. Left and right is on and off, but you can also press down to bail an automatic set. And that was what I was talking about in train handling. So if you set up the automatic, you want to go and bail the independent to make sure that you're not braking from the front and causing the whole train to run into you. It's pretty important, especially when starting your sets. As such, the actuating hose allows that to happen. The second input axis that the engineer has, pressing down on that handle, sends a message via air pressure over this hose to the rest of the braking system on the rest of the engines, and it independently from the actual independent axis tells them then to bail off. Here's the automatic brake valve, and here's where I'd put my independent brake valve if I had one. Yeah, our independent brake valve handle is missing. It's one of those things that we're working on replacing as we restore the locomotive. We'll get one eventually, but it didn't come to us with one, and that's that. A lot of times when railroads donate stuff, maybe it's complete, maybe it's not. If you were to imagine a handle here, as you move it to the right, you go to apply, move to the left, you go to release, and then pressing down, you can see in that slot how there's vertical space. Pressing down is what actuates bail off, which releases the amount of independent brake pressure that was applied by the automatic as you move the automatic over. It'll leave the independent set up to whatever position you left the handle at. So if you were at 25 pounds, somewhere in the middle there, you bail down, it's only gonna get rid of whatever you added with the automatic. It won't go all the way to zero. Additionally, on the air side, you'll note that there's the two sets of those three hoses. We know what each hose does, and they're duplicated on each side. The reason behind that is that the brake pipe is the only hose that can really run as something solely in the middle, and adding more things around where the couplers are doing the dance doesn't really allow for the flexibility in keeping all the connections together. So the connections had to be further outside, and with locomotives being able to be positioned either way, forwards or backwards, you had to have two separate sets, and you only need to have one of the sets hooked up. That said, it was standard based on railroad rules and rules of the Air Brake and Train Handling Guide that if the weather's really bad out there, it's a good idea to have both sets hooked up in the event that there's significant leakage in any of the hoses. As well, the valves to cut out or cut in the three distinct MU air hoses we have are located behind the end sheet, tucked right behind on those lines so that they're out of the elements. Now, once you've got that electrical cable plugged in and you've got all the hoses mated up and all those valves open, there's still a couple things you have to do to set up the locomotives as a proper consist. Something that we always called test out at the shop, putting the engines together, testing everything, and making sure that the train's gonna behave like it did. It was our final kind of quality assurance thing. We usually did it on third shift at my shop because we were just a small location. The specific things that you have to set up in here are the headlight control switch to make sure that your headlight controllers are actually train lining through all the locomotives. And then as well, you have to have the right breakers up on the control stand. Specifically, the engine run, generator fields, and fuel pump breakers must be up on the leader, and they must be down on all the trailing units, because we're going to send those signals through that electrical cable. Additionally, the reverser has to be out of any trailing units. You can't have a reverser in. The reverser is kind of the key to the locomotive. If there's a reverser in, you're going to be doing something, and that's not good to have on your trailing locomotives, because they don't know if they're trying to listen to their stand or the leader's stand. You get your headlight switch set up for whichever way the consist is set, whether you've got engines ahead of you or behind you, depending on what direction you're going, all that sort of stuff. There's controls for that so that your front headlight switch and your back headlight switch control whatever the front and back headlights in the consist are. The locomotives are aware that they're getting signals through the MU cable itself. If a locomotive is in the middle of the consist and you set it to single or middle on the switch, it knows, hey, I'm getting stuff on either end. I'm gonna pass whatever headlight command I get to the other side. There you go. That way, when you turn your headlights on and you turn on the backup light, you don't blind your conductor as he's walking through the consist accidentally, which has happened a couple of times. Headlight switch, engine run, generator field, and fuel pump switch, and then as well the reverser, whether it's in or out, and you're ready to go. Most of those are self-explanatory, but if you're not familiar with what generator field is, it is specific to the actual fields themselves within the main generator or main alternator, depending on what your locomotive has. If generator field is down or it's off, there's no way that you can actually generate any electricity via whatever method it is and supply it to the traction motors. So that's something you interact with a lot as an engineer. If your conductor's got to go in between and hook up hoses, anything like that, part of three-step protection is turning off that field, making sure that even if the engine does spool up for some reason, you're not going to generate any electricity because you're not allowing the generator or alternator to do so. A lot of people have asked, why do diesel locomotives have notched throttles? And it's partially because of the logic that was put into MU. It developed over the years, and it took a long time for the modern standard that we have to be fully realized. Because EMD was the primary manufacturer of diesel locomotives who did a lot of the development back in the day, they picked an 8-notch throttle with 5 governor solenoids. That's what went into MU, and that's what everyone else ended up having to match. It's a neat system, and it makes sense when you're thinking about that discrete logic. The 8-step throttle is really actually a 9-step throttle, because idle is technically a valid position as well. And depending on what notch you're in, it's going to call different solenoids in the governor. Recall that early diesel locomotives, including this one, have a mechanical governor that sets the speed that the diesel engine runs. Modern locomotives are all electronic fuel injection, computer control, the whole thing. You get the idea. But back in the day, mechanically, we had to set what the engine's speed was going to be, and it was easy to do that just by interacting with what the governors had. A couple solenoids to say, hey, speed up by this much. The solenoids are referred to as A valve, B valve, C valve, D valve, and E valve. Depending on what throttle position you're in or in idle, it's going to call one or a combination of those valves to set the engine's speed between its idle speed and its max RPM. And fun fact on these diesel engines, they run really slow. They run probably slower than your car does at idle regardless. Full speed in this engine, I believe, is 902 RPM. On a Dash 9, it's the fastest I've heard of on these big diesel locomotives. It's 1,050. That's it. That's full throttle. That's 4,400 horsepower in that case. This engine, 3,000 horsepower at 900 RPM. There's some big pistons, that's for sure. But because of that mechanically governed nature, we had to give very simple commands, and that's what we ended up sending. And that's what ended up getting sent to the other locomotives, because that's all we had. And that's still the modern standard, despite the fact that we have all the electronic control we do. It's beneficial because it's simple. Rather than sending some sort of variable that would need to be determined or read by another locomotive and another computer, and you're adding more digital nonsense, you have a discrete on-off. Go to this state. And that is simple, it's easy, and it's safe.
All right, well, I hope you're ready for Nerd O'Clock. We're going to go through the pinouts of that 27-pin cable. The first pin is pin 1. And it is the power reduction pin. Power reduction is specific to reduce the output power at a certain throttle notch if the consist is struggling with traction, a wheel slip kind of thing, that sort of thing. Pin number 2 is the alarm bell. And that is, hey, one of the choo-choos is having a problem. I need to tell the leader and everybody else to sound the alarm bell so you can go and troubleshoot what's going wrong. Pin number 3 is the D solenoid in the governor, D valve. This gets into the throttle that we just talked about. 8 different notches plus idle, and you get the 5 different solenoids to control them. Pin 4 is the negative common voltage. It's really important for any sort of computer control, anything of that variety, that all of the voltages along things get shared, so the locomotives will pass that through from the leader back. Pin number 5 is for emergency sand. An emergency sand is you've dumped the train, you've put it in emergency. Do you want sand to be deployed or not? Typically yes, because that'll help you stop without sliding the wheels, stop as fast as you can. 6 is gen field. There it is. So you want the switches down on the trailing units because you're going to send that, and you're going to be able to protect people with that same 3-step protection from one switch rather than each unit's individual switch. 7 is the C governor solenoid, and 8 and 9 are a pair. They get interesting. Reverse command or forward command to let the locomotive know which way it's going to run. So when you throw the reverser forward, you're going to train line forward command. There's a cheeky little trick that they did in wiring the locomotives to make this make sense. Inside the MU cable itself, pins 8 and 9 are swapped. If you're to hook locomotives back to back, it means that locomotive A's pin 8 would get connected to locomotive B's pin 9. cable swaps it over. You couple that with the fact that the MU pod on the front of a locomotive versus the rear also has those same 2 pins switched, and very quickly you can understand, oh, if I have 2 engines facing that way, it means, okay, this is the leader, he's gonna pass back pin 9. We're in forwards, it's gonna switch to pin 8 coming into the next guy, but because pin 8 on the front is now forwards, the locomotive knows it's going to go forward. It's a little bit of a neat trick to know the directionality of the locomotive with only having the 2 pins. It's pretty smart engineering. Number 10 is the wheel slip indicator. If any unit tosses wheel slip, it'll tell the engineer. Number 11 is just a spare port. There's nothing sent through it. 12 is B valve. Number 13 is the combined control circuit and fuel pump breaker. They're tied together. 14, another spare. 15 is the governor's A valve. 16 is engine run, switch to make sure that the engine can do more than idle. 17 is your dynamic brake control signal to make sure that dynamics are allowed and a thing that can happen. 18 and 19 are 2 more spares. 20 is a dynamic brake warning if you're having an issue in dynamics that needs to be communicated to the engineer from any unit. 21 is the dynamic brake interlock to make sure that locomotives are not trying to load and also brake at the same time. 22 is the air compressor control, so recall that the main reservoirs are tied together. You could regulate each individual air compressor on each unit, but on a longer consist, if the locomotive can electrically send a signal, if the pressure is just a little bit less on that lead unit for some reason, it'll start the other units pumping up faster and shut them off at the right time. 23 is manual sand for engineer deployed sand. 24 is the dynamic brake excitation. Excitation being an electrical signal that can then be amplified into more electricity. In order to cause the traction motors to function as generators, they need some kind of excitation to start, much like an alternator in terms of a car or in terms of a large EMD locomotive that's a little bit more modern. You have to give it an electrical signal that it can then take and turn it into a larger, more powerful signal. It's called excitation. 25 is the headlight. Do you have headlights on or not? And what you do with that is based on the switch we talked about. 26 is the ground relay reset. Ground relay is the high voltage ground relay. And that is never a fun time when it comes on and it means something. Sometimes you'll get false ground relays based on moisture or other things if the locomotive's been sitting out and all that. But it means, hey, something in our high voltage electrical, so between the alternator and the traction motors, something has gone awry and we're trying to turn the locomotive into a welder. We don't want to weld with the locomotive. That's not good. That's how you zap things and break things and all manner of badness. If you keep getting ground relay tripped, you want to know, hence why, hey, trailing units, if you're going into ground relay, please tell me. And then lastly, pin 27 is also a spare. So we have many different functionalities that we can pass across and a bunch of spares as well.
Each of those 27 pins is a different connection for a different electrical signal that flows between all the locomotives. And almost all of them are actually just a binary signal. Is there voltage or is there not? And that voltage, fun fact, is 74 volts, which is what locomotive batteries are. Why is it 74 volts? That's something I actually don't know. The electrical side of locomotives is definitely something that I've been trying to learn a little bit more about and I never really got exposed to. If you know, let me know down in the comments below. I'd love to learn. If you see 74 volts as a trailing unit, you know that that signal's active and you're going to act upon it. Now you might be wondering why there's so many spare pins in those cables. It's not like you could rewire one of those important circuits to one of those spares in a cable unless you did it to every engine in your fleet and then you couldn't run with anyone else's engines because the rest of them would still be using the pins as allotted. The reason for the spares were for railroad-specific features to be added. And there's actually a really cool feature on this specific locomotive, Denver and Rio Grande Western 5401, again at the Colorado Railroad Museum. This is something that is so cool that I wish more locomotives had, because operationally as an engineer, it makes a ton of sense to me, though I'm used to running with passengers and I have heard that freight does not complain, so being as smooth may not be the important thing. And what I'm talking about is that there's an actual power reduction dial on the control stand that does MU to the whole consist. So you could leave your power throttle in run 8 and you approach up to a signal working up against the grade, and you could dial the power down evenly and smoothly until you came to a very nice gentle stop. Then apply all your air, make sure you're holding against it, shut the power off entirely, and there you go. Rather than playing with a step throttle, is notch 1 not going to be enough? Is notch 2 going to be too much? That's a game that you learn to play when you have a step throttle diesel. Sometimes that's too much, not enough, and you have to modulate with the brakes. But in the case of the Grand, they passed that signal for that power reduction switch all the way down to each unit, and you could toggle it on or off. Do you want to send it down, or do you want to just dial down just your lead locomotive? It's a really nifty system, and it made a lot of sense for a railroad that dealt in a lot of mountain grade territories like the Grand. Now lastly, we briefly talked about distributed power in the intro of the video, talking about how you power the locomotives at the end of the train. And the way it works is that there's a special dedicated set of radios. Like, we have a radio that already talks from the front of the train to the back of the train, with a head-end device and an end-of-train device, which have a million slang terms, which of course they don't teach you when you go to the railroad. You kind of have to learn them. People have heard the term FRED for the end-of-train device, the flashing rear-end device, or something else, depending on how railroady you are. But at least in our terminal in Seattle, the slang was a Mary for the front, because you had a Fred and a Mary, and then therefore they were together, and it was a cute couple thing. Whatever. I had the trainmaster call and ask me if I had a Mary, and I was not sure what planet he was from. And then I eventually learned, as you do. But we have a second set of radios just like those that can talk to other locomotives on locomotives that are so equipped. A lot of these more analog locomotives, like this SD40T-2 that doesn't have any of the computer control nonsense, did not support distributed power. That said, you only need a leader and one engine in the rear consist to have DP as a functionality. You can still then MU the rest of those locomotives and set it up like a lead locomotive as you normally would. And as far as how the engineer actually works with distributed power, I understand the concepts, but I've never seen it. I worked mechanical. I never had to set up a DP consist. So if you're a Class 1 engineer, you've been there, done that, let us know in the comments down below. That's out of my wheelhouse, but very much in your wheelhouse. Distributed power, they find that they can get more tonnage out of the trains when they set the locomotives up that way. And as well, you have better control over what the slack action's doing because you have locomotives at both ends. You could have the trailing set of engines braking while the lead set of engines are pulling to keep things in tension, perhaps over some bumpy territory. It's a real neat piece of technology, and a lot of railroads are really utilizing it these days, especially when you're talking about trains getting longer and longer, and maybe even adding extra sets of engines in the middle. It's a very important piece of kit for the railroad these days. Anyways, guys, that's a little bit about how one train crew can run many different locomotives. The technology behind it's pretty cool, and it allows us to run some really big trains over here in the States. We're definitely different than the days when you had to add another crew, another engine, or double head steam or anything like that. It's quite different. Anyways, guys, I hope you stuck around, I hope you learned something, and I hope you thought it was interesting. As always, thank you so much for watching, and we'll catch y'all next time.